Hi, and welcome to Chapter 7 and 8. Every economic evaluation involves use of mining equipment, whether fixed or mobile. There's a capital cost of owning this equipment as well as operating costs of running it. This chapter looks at ownership cost. This chapter sets out to understand the equivalent costs of owning equipment. It involves the capital cost, life of the machine, and other costs of ownership. Three alternative methods are presented for working out the hourly ownership cost. These are the average investment method, the equivalent least cost method, and the discounted average cost method. Before the three methods are described, an important distinction must be made between the terms accounting life, operating life, and economic life. Accounting life is the life over which the machine is depreciated for tax purposes. It is the rule that the tax authorities permit a company to use in working out its taxes. The operating life is the life over which the mine operator expects the equipment to operate and at an availability satisfactory to meet production targets. The operating life is usually similar to the economic life because if manufacturers are finding that their machines are being superseded before those machines are worn out, then over time they change the design to bring the operating life into line. The economic life is the life over which it can undertake its defined task most cost effectively than alternative ways of accomplishing that task. In a world of unpredictable change, equipment that is less flexible or less adaptable is more susceptible to shortened economic life than is more flexible equipment. Okay, so now we will cover the three methods used to figure out the hourly ownership costs of equipment. The first method, the average investment, is used by many equipment suppliers. It has the advantage that the calculations are very simple, but it's also fairly imprecise. The average investment method has two components, one representing the wearing out of the equipment and another representing the return on the money the company has tied up in the equipment while it is operating. If you look at the example that is provided on page 97 and 98, and you can see how this is done. Remember, this method, while simple, is not as accurate as the other two methods. An alternative and preferred method is to treat the plant as if it were being leased. Lease rates include all of the factors considered in the average investment method, but they more correctly account for the higher interest component of the cost earlier in the equipment life. The example on page 99, example 7.3 of the text, and you look at that to see how this is calculated. The discounted average cost is the price per unit of production that you would have to pay for an independent operator with the same investment criteria as yourself to undertake the production. Page 64 of the text in chapter 5 has more information on this. The example on page 101 can be compared to the others in this chapter. One significant advantage of the discounted average cost method is that it allows direct comparison of owned equipment with hired equipment. If a contractor will place $1 million machine on hire for $150 per hour, then the equivalent cost of the same machine in the mining company's own hands is the operating cost per hour plus the discounted average cost as determined by this method. Before any economic analysis or decision-making can be undertaken, the operating and capital costs of equipment must be estimated. So equipment costs vary between mine sites, and there is no cost that can be applied universally. So that's the situation with Chapter 8 and the operating costs. So operating costs can be sourced from mine statistics, equipment suppliers, contract quotations, or first principles. And equipment costs normally are stated as a cost per operating hour. So the term first principles refers to the fundamentals or the basics. Building up costs from first principles demands a systematic consideration of each component of equipment operation. This example or this figure is figure 8.1 on page 104. This illustrates a typical breakdown of the operating cost of a large rear dump truck and a large front-end loader. And then below that in Table 8.1, the standard presentation of cost is an amount per operating hour. The next few slides cover the many different components of operating costs. In other words, the first principles, the building blocks that make up operating costs. For electrically operated equipment, there are infrastructure costs and then the actual energy usage and the demand charges. Demand charges reflect the cost of the utility providing high power for short periods of time. There's an example on page 111 of your text that shows how these numbers fit into an electrical operating cost per hour. Fuel costs are based on the cost of fuel, the engine's fuel consumption rate, which depends on engine power and duty cycle, and working conditions. A truck hauling on a long loaded uphill haul will have a higher duty cycle than a truck hauling on a short flat haul. Lubrication costs can usually be calculated as a percentage of the hourly fuel cost. These proportions can vary based on the proportion of hydraulic components on that piece of equipment. Tire costs apply to rubber-tired equipment such as trucks, front-end loaders, rubber-tired dozers, graders, and light vehicles. Tire costs are obtained by the total cost of the tire multiplied by the number of tires and divided by the hourly life. Tire manufacturers provide the guidelines for calculating hourly life. The example on this slide comes from page 114, example 8.4. The cost of repair parts is one of the most difficult to calculate. If no historical data are available, there are two commonly used methods of estimation. The first general formula, which is appropriate for large equipment, such as shovels, drag lines, and crushing conveying systems, involves multiplying the capital cost by a percentage and dividing this result by the number of operating hours per week. Typical values range from 3% for conveying system consisting of structural work to 10% for a bucket wheel excavator, which has a much higher proportion of machinery and moving parts. A second method uses an hourly repair factor or repair parts factor. This method is widely used by equipment manufacturers for smaller equipment and assumes that the equipment is a collection of spare parts. We also must make allowances for specific site conditions. Trucks driving on well-made roads will be subject to less stress and longer component life than trucks driving on rutted, poorly maintained roads. The adjustment factor can range from 0.8 for well-maintained roads to 1.2 for poorly maintained operating environments. Wear items include bucket teeth, hoist ropes, drag ropes, dump ropes for drag lines and shovels, and other items typically referred to ground engaging tools. Major overhauls cover the cost of major component exchange or rebuild. This can be estimated as a percentage of initial capital costs, such as 15% every 12,000 hours, or else a buildup of components in their lives. For large semi-mobile equipment such as drag lines, drills, and shovels, major overhauls are commonly scheduled every 5 years. The tables on page 118 and 120 give some good examples for this slide. Labor costs are typically calculated on an annual basis. Subsequently, they are broken down into a rate per hour or a rate per week. For a whole mine study, operating labor requirements are usually built up from two components. One, labor directly associated with equipment, and two, labor that is a function of the task being undertaken. In surface mining, almost all operating labor is associated with equipment, whereas in underground mining, most operating labor is a function of the task. Operating labor cost factors include shift rosters, some industrial practices that might require extra staffing for safety reasons, and absenteeism, which includes accounting for annual leave, sickness, and training. At the end of Chapter 8, page 124 and 125, there is a sample owning and operating cost breakdown for a hydraulic excavator. Exercise 3 for this week will have you do some calculations for a front-end loader. There is a lot that goes into costing equipment, which is a very important mining economic component in a mine plan.